Hi, my name's John Downing, and I'm a limnologist and aquatic ecologist. I am the author of this course. Today I want to talk about, for session 7 of Aquatic Ecology, I'd like to talk about the origin and evolution of streams, and we'll keep on talking about that material in the next session as well as we look at how streams are structured. But I thought we're going to also talk about how lakes and ponds are evolved and created, and so I thought I'd start with streams, the running water first, and we'll go through some elementary aspects of it anyway, and hopefully pique your interest, so that you might want to go and learn some more even about it. It's quite a fascinating area. Luna Leopold, a very famous geomorphologist and geologist, once said, "Rivers are the gutters down which flow the ruins of continents." And it's not literally so. Rivers are important unto themselves, but they are one of the major forces that forms the geomorphology, or the shape and form of land masses. And so I've been long fascinated by the formation of streams. In fact, I think most students who are interested in aquatic ecology and limnology have played in mud puddles and built stream systems before, but I thought I might show you a really brief video, and if you're interested in more, you can have a look at YouTube and look for analyses of stream tables. This is a little video that covers a stream table, and you can see how the rivers and streams are formed as these students mess around with them in a sort of a microcosm. Whoops. These are plastic beads of different sizes, colored in different ways, and they put drips of dye in the water every once in a while just to see where the deep water flows. And they're having a lot of fun, a lot more fun than you ought to have in class, but makes me want to have one of these stream tables, really. You can see how they try different kinds of approaches to see how the stream forms and changes over time. Here they built a large dam. Look at the dam erode through groundwater flux, and it breaches. They put large landforms in the way, erosional blocks. I think we're about to see a major flood. I think I could spend a long time fiddling around with this, but what's interesting is to see how the river changes its shape and form depending on flow and any other kinds of obstructions that there are. Music is nice too. Yeah, so rivers are the gutters down which flow the ruins of continents. It's a very, very important study, and we'll go through only the briefest introduction to it, and I hope that you'll find it interesting. My objectives for this session are to learn the process of stream formation, and then see some stream networks as an evolving system, and learn the important processes involved in stream formation. Also learn the factors driving stream evolution, how they change over time, and how they change landforms over time. And then briefly talk about how stream patterns reflect underlying geology, and then in sort of sum to learn the differences between youthful low-order streams and see how they differ ecologically from mature higher-order streams. So stream order is something that we've already talked about in a previous session, but I thought I'd go through this again because it's a pretty important set of concepts. This comes from Horton and Strahler's work back in the last century, and they basically divide the sizes of streams up into a series of different levels and grades, so that the first order streams are the smallest permanently flowing streams, and those you can see up in the upper reaches of this sort of dendritic or tree-like pattern. In fact, trees branch very much the same as streams do and follow some of the same rules. And then as you bring together two streams of order of the first order, you form a second order stream, and you can see that up here in the up here, these first order streams, two smallest permanently flowing streams come together, and at their confluence they create a second order stream. Another second order stream flowing down here connects with this second order stream and creates a third order stream. So the union of two streams of order n creates a stream of order n plus 1, and so on and so forth. And you may wonder about how far we go. I think about the highest order stream in the world is a 12th order stream. So, but the order of streams determines really kind of a lot of the characteristics of it. And so this is one reason we pay attention to it. It's not a perfect concept, of course. You can have a large first order stream. You can have a smallish 10th order stream. But in general, the order of streams indicates a substantial amount about the way they function. So, the evolution of streams and rivers is the principal force modifying geological landforms. And basically, much of the science of geomorphology is a study of how the action of water modifies landscapes. And if you'd like to see more of this, there's tons of stuff on YouTube about geomorphology, and actually about Davis and the Davis Geomorphic cycle is what we're going to be talking about for the rest of this little session. And then the formation, you should remember that the formation of streams is a totally dynamic process, so stream conditions vary across time. And that's basically the concept we're going to exploit. So there are a couple of kinds of streams that are most important. Geomorphologists define several sorts, but we're going to concentrate on the first two, consequent streams and subsequent streams. So consequent streams are the first streams to begin in sort of a new terrain, and if you're playing around with a stream table, you know, the consequent stream is the one that eventually finds its way flowing downstream through this rough yet flat terrain. And they basically follow random contours of the rock, and they flow parallel to the tilt of the rock or parallel to the tilt of the land. So these will basically be quite meandering and bump around, finding their way through the weak places along the surface of this new environment. A subsequent stream comes along a little bit later, and they tend to follow weak places in rocks and later predominate because they can cut down rapidly and capture other streams. So those are the two we'll think about most. And then there are obsequent streams and insequent streams, but we'll pay less attention to those. It's just important you know that there are a variety of different kinds of streams in the geomorphic sense. Now we'll look at the Davis geomorphic cycle, and this is a very elementary idea set. It's a precursor to several more advanced models, but it's still a very important one. There are many more modern approaches with more detail and versatility, but the Davis approach was one of the most historical and really easy to understand, and it contains some of the basic elements without too much complexity that might impede understanding, and that's why I concentrate on that in this limnology course. So there are several steps in the Davis geomorphic cycle, and we'll start kind of step one in the youthful period, and this is imagining some kind of terrain that's newly emerged from, say, beneath the sea, or maybe beneath a large glacier or something. Its surface tends to be irregular. It has bumps and depressions, and you can think back to that stream table and see how they, even though those students were smoothing out the surface, they were it was still quite rough. It had bumps and depressions, and of course it's slightly tilted because there's nothing in the world that is perfectly level, it seems, except for perhaps the sea surface. Rain falling on the land then concentrates in any depression, and that will form lakes and ponds, and then they begin to spill over and connect together until they spill into a drainage system that continues downhill until the water has no further potential for movement. That is, when it gets to sea level. Then the only way it can move out of the sea is, as we saw in one of the earlier sessions, is to be evaporated and then precipitated and drop back down and complete the hydrologic cycle. Streams of this type are called consequent streams, and they predominate in any kind of early stage of the cycle or early stage of fooling around on a stream table. So in step 2 of the geomorphic cycle, however, the consequent streams change from having long profiles that are irregular, and they do this first near the mouths and then progressively upstream, and work their way through softer material. And sometimes they will simply go around resistant surfaces. The attempt is for them to get down to base level, which would be sea level, and at which point they have no further potential energy. And so the down-cutting occurs first downstream and works its way upstream and begin to smooth out the profile in creating subsequent sorts of streams. So as the downcutting takes place, the consequent streams get deeper, and they begin to capture adjacent ones. And you can imagine this simply by looking at this stream downcutting through this material, eventually merging with these streams over here. And they begin to capture streams and create diverse kinds of flow patterns. So in step 4 in the Davis geomorphic cycle, as weathering proceeds, the subsequent streams, these are the streams that have followed soft places in the rocks, capture the flow of some of the consequent streams, and then they broaden out the stream network. This increases stream order because the first order streams are combining together, and it shortens the amount of the stream network composed of first order streams. So basically begins to make a more complex sort of stream system. You can see that here where consequent stream 2, C2, was captured, the upper reaches of it were captured and merged into C1 eventually by following this subsequent stream that was flowing somewhere along this fault. This increases the stream order, doesn't it? Because you've added this stream to that one, making a second order stream. We have a second order stream here flowing into this stream, whatever its order might be, working its way downstream and increasing the complexity of the flow network. Now, as stream order increases, the rivers have less downcutting power, but they tend to move laterally. And when they move laterally, they create floodplains. And I show this picture on the right of water droplets because you probably have all sat in your car on a rainy day looking out the windshield and watched the drops run down the windshield. And you may notice that they only rarely will flow in a very straight line. When they have sort of low power, they tend to be deflected from one side to the other and begin to make sort of meandering flow paths as they move down the windshield. Now, if you tip the windshield higher, you'll increase their flow potential, or you increase their potential energy, and this makes them move faster, and they tend to move in straighter flow paths. So as you move from A, B, C to D, and we are beginning to meander more and cut out here laterally, cutting out laterally, and increasing the stream meanders as the stream becomes sort of slower and broadens out through its floodplain. So creation of floodplains is a natural part, really, of the stream aging process, and that means that, of course, the stream moves out and forms a broader and broader and broader valley in which it flows. So, looking at step 6, as the cycle progresses, the rivers pass from high gradient streams in narrow valleys to low gradient streams in very broad valleys due to the lateral cutting of streams. And here you can see this in profile as if we've taken a time and space cut through the profile of streams. Here you see very narrow valleys in the youthful period. Youthful period here. They cut down into early maturity, much deeper valleys. And as we get into the old age or late maturity, then we'll have hills, sets of hills or mountains, divided by very broad valleys containing low gradient meandering streams. So there are lots of geological processes that modify stream channels, and we should learn a few of them, at least learn their names and understand what they are. Downcutting is this valley deepening process that's caused by stream bed erosion. And if you run water through a bed of sand, you can see this. It immediately begins to pick up particles and move them downstream. So it is downcutting, making a deeper and deeper groove in the landscape. Now, lateral erosion is this valley widening process that's caused by undercutting banks and bank erosion. And if you've ever canoed or boated on a small stream, you can see this in action. You see the undercut areas at the big bends of the meanders, and you see depositional areas forming riffles in between the big stream meanders, and they meander across the valley floor, picking up sediment and moving it laterally and redepositing it and creating large deposits of alluvial sediments and rather wide valley floors. Now, another process that's really important, it's gotten really important as we modify streams, is something called head cutting or headward erosion. It sounds a terrible word, but it's basically the uphill growth of a valley that occurs via gullying and mass erosion and sheet erosion, and this it results in valley lengthening and a decreased gradient and approach to the base level. And this occurs anytime we speed up water or cause it to flow away faster. So in agricultural areas, for example, where we tend to straighten streams to move the water away, one of the consequences of that is we're causing those streams to head cut or lengthen their profile upstream, farther and farther upstream, because we've simply sped up the water, which allows it to hold much more power and much more energy for creating erosion and moving sediment. So there are several stages in the Davis geomorphic cycle that are worth remembering. In extreme youth, the stream just simply begins downcutting. The valley walls are steep. Rapids and waterfalls are generally numerous. In youth, we still see rapids and waterfalls, but you begin to see massive erosion and sheet wash that erode canyon walls, and these create V-shaped canyons, and the energy is downcutting the channel relatively rapidly. In the mature stage, then, lateral erosion widens valleys, and floodplains develop, and the channel becomes meandered, and this can sometimes occupy the entire valley width. Simply a meandering river working its way through an entire valley. And in old age, then, the valley is wider than the meander belt, and the meandering of the stream deposits alluvium over the valley, creating smooth, flat surfaces. So, in geomorphic evolution leads to increased stream order. So, when looked at another way, here we have first and second orders flowing into the sea. We have a fault cutting across it, and we know that as we go from consequent streams to subsequent streams, then we're going to cut along the fault, and we'll tend to see stream capture. Well, that's what's happened here, as you see that the stream on the far left is no longer a tributary of the far left stream flowing into the sea, but it begins to move across down the fault line through the sort of a weak place in the uplifted surface, capturing other streams and causing an increase in order, in maturity. So streams are cutting down toward base level, and this moves the lower reaches upstream. Stream capture from downcutting aggregates streams, and higher order streams then dominate in mature landscapes, and then the lateral erosion over time leads to lower relief and basically broad valleys that are separated by ranges of hills or mountains. Now, another thing that can form streams is glaciation, and a couple of different kinds of glaciation form streams. Alpine glaciation is a pretty important process in the mountains, and here you see some U-shaped valleys that have been cut by glaciers, and streams will run down through those U-shaped valleys, occupying the bottom of the valley. We also will see things like rock step lakes separated by little interconnecting streams. Also, cirque lakes will form up here, and we'll be talking about those in future sessions. Basically, alpine glaciation is important also in mountainous areas in creating stream networks. Here's an alpine stream channel just to give you some sense of what they look like in reality. And here you see the glacial U-shaped valley, and down in the bottom of it, a very nice little stream flowing, which is the remnant of the glacier, which has probably receded upstream. Continental glaciers also influence stream formation, and this is an image that I've taken out of a textbook showing the remnant of a receding glacier. Now, these receding glaciers could be a kilometer and a half thick or more, and so they were very, very heavy, but they'd be melting, and water would flow out underneath and flow out, creating other stream channels. If you look around where you live, you'll probably find some of these rivers that were, especially if you can locate the site of an ancient glacial lake. The big rivers that flow out of them were probably formed in this way. Now, there's kind of an error, in my view, on this graphic, in that they have the stream branching backwards. And that can happen in some areas where you form essentially a delta, and the water sinks down into porous sediments. It occurs in some places in Texas and elsewhere, but likely simply a drawing error in this particular book. But continental glaciers can influence stream formation. The Minnesota River, for example, near Minneapolis, St. Paul, just south of the city of Minneapolis, it has a gigantic river valley that once flowed full by draining Glacial Lake Agassiz. So it can be a very important river forming process. And here you see some of the water flowing out from fairly large glaciers. This isn't a continental glacier. We don't have that many of them anymore, and we're melting them pretty rapidly as we change climate. But it gives some sense. There's quite a lot of water that flows out from the edge of a glacier, especially during the season of melting. The region I live is the Midwest U.S., and of course we see quite a lot of this the influence of glaciers. And we were influenced by this very large Laurentide complex about 12,000 years ago that left a lot of sediments and created a fair number of river networks as well as lake networks. Other processes that form streams would be things like chemical weathering, and in areas where there's a lot of limestone and acid or acidic precipitation, which is almost everywhere if there's carbon dioxide in the air, you will have precipitation fall on the ground. It forms a weak acid, carbonic acid, but that acid, as it percolates down through the rock, then mobilizes calcium carbonate. And this is actually what forms stalagmites and stalactites in underground caverns, but it also tends to form sinkholes, and those sinkholes begin to connect together and also can form river networks over time. So stream evolution is driven by a large number of factors, including tectonic activity, climate, geological age, glaciation, and chemical dissolution. So Tectonic activity has an effect because the upleaf increases relief and folding and fracturing that changes the landform that the streams will follow. Climate is important because you clearly get more erosion and evolution of streams with high precipitation. Of course, more water will move more material. Geological age is important also. Stream order tends to increase with time since uplift. And glaciation is important. Both Alpine and Continental glaciers can cut stream channels and deposit uneven sediments on landforms. And finally, chemical dissolution. The karst cycle can accelerate topographic change through dissolution of calcium carbonate. So stream patterns also can reveal geology to you, and there are three major kinds of forms. You can look on Google Earth and other places to find different stream patterns. They're quite fascinating to see. But there are three main ones that we see. Dendritic is kind of a standard ramifying kind of form. Dendritic meaning it looks like a tree. There also are trellised stream networks and radial flow. So dendritic is the dendritic ramifying patterns suggest fairly homogeneous continents because the formation is working like a tree basically, and connections are made in a fairly sort of uniform substratum. In trellised formation of streams is a result of gently dipping faulted terrain or valley and ridge patterns that you may find after a large period of erosion. And radial flow patterns form around domes and hills, and I'll show you a couple of those now. Here's a kind of a standard dendritic looking stream channel. Looks very much like a craggy tree, and this is in a fairly uniform substratum. Here's a trellised network, and this trellised network is seen around, well, in this case, in the Appalachian plateaus and Piedmont mountains. So you have a series of trellised areas and some trellised areas of streams sort of oriented along the mountain ranges, and then some water gaps where water flows through. So it's a fairly standard kind of flow pattern that you'll see in geology that has been processed in this way. And finally, radial stream structure. Here's a three-dimensional reconstruction of a volcanic cone, and you can see these radial streams flowing down, making erosional surfaces and stream patterns in any place that we have a massive uplift. This particular one is in Hawaii. I have worked in Iowa for quite a while, and this is a stream pattern that we see in this region, and you can see it's fairly dendritic, or at least it was originally until people began to improve drainage. And this was a recently glaciated area, so it was fairly homogeneous, a homogeneous sort of sediment, and so you'd expect a trellis stream network. So youthful low-order streams, in youthful low-order streams, the discharge may be low because they drain a small watershed, but flow velocities are often high. The word watershed I use interchangeably with catchment, although they aren't perfectly identical. But watersheds and catchments, where they're small, oftentimes they collect little water, but flow velocities can be rapid in those youthful low-order streams. The bed sediments are often coarse because finer ones are washed away, and that's a kind of a standard aspect of stream formation. If you find heavy rocks and boulders, then you know that the stream flow usually has been very rapid, because it has washed away the sediments that are smaller, washed them downstream where they deposited when the when the power of water flow became less, probably in a valley or delta somewhere below. Also in youthful low-order streams, the channels are straight with a fairly high gradient. They're quite tilted, and seasonal variation leads to floods, erosion, and drying cycles. In contrast, mature, high-order streams, the discharge is often really high because the higher-order streams collect a lot of water from a very large catchment area, but velocities tend to be fairly low. sediments tend to be deposited with net transport nearly equal to zero. So sediments tend to be quite fine in these mature higher order streams. And channels have very large meanders, and this lowers the gradient and flow rate and allows deposition of materials as well as meandering of stream channels across valley floors. Seasonal variation tends to lead to floods, wetland creation, and larger floodplains. So as a summary of this session, first, stream formation and erosion form continents and change the landscape substantially. The streams in themselves are very important, and they evolve as landscapes age. The important processes to remember are downcutting, stream capture, lateral movement and meandering, and changes in gradient, head cutting, and changes in order. And it's important to understand those concepts. Stream evolution is driven by tectonics, originally by climate, offering different water regimes, by glaciation, chemical dissolution, which is a function of underlying substratum, and erosional processes. Stream evolution alters habitat and sediment. Stream patterns reflect the underlying geology, and you can pick that out when you're flying in a plane the next time. Get some pretty good ideas about what kinds of terrain you're flying over based on the stream patterns. Or look on Google Earth and look around the world at the different kinds of stream patterns and draw your own conclusions. And finally, it's important to distinguish between youthful low-order streams and older age streams because they differ ecologically from the mature higher order streams. So the two various stages of the geomorphic cycle give rise to different kinds of flow regimes, different kinds of patterns, and very great differences in ecology.